Alrighty, folks, and we are back. Left off talking about the sun's angle in the sky, and moving on here to talk about the North Star. This is interesting. You've heard me use the words relative a few times. It's relative to this, relative to that. The North Star, which is currently called Polaris, by the way, if you stand at the North Pole and look straight up at the literal North Pole, look straight up, it is the star that is overhead. For us, here in Utica, or someone else who lives further south, the North Star moves closer to the horizon. At the equator, it is exactly at the horizon, and in the southern hemisphere, well, you can't see it. So this is something I've always wondered. You know, I've read through it in textbooks half a dozen times, of course, but you know, using stars for navigation and just blows my mind. I know people do it. I know there's special tools to help you do it, and so on and so forth. But this one, you know, at least you could help with your latitude by gauging how high the North Star is up in the sky. You can tell how far north or south you are. Pretty neat. And speaking of neat, oh, no, we got one more. Well, sort of. It's at the end of this slide. The neat thing I was going to tell you about. The Earth wobbles on its axis. Some people know this, some people don't. It's not a, kind of like when a top comes to a, just before a top falls over. Okay, you've all spun a top, I hope, or a gyroscope, or anything that spins like that. You know that towards the end of its, before it runs out of energy, it starts to vary a little bit, wobble a little bit. And I'm not implying by any means that the Earth is about to run out of energy, but we do have a bit of inherent wobbling. This wobble has been long-standing, and it brings us right back to where we were 26,000 times later. All right, so there's a 26,000-year cycle of the Earth's pole wobbling just a little bit. And the neat thing about that is that Polaris hasn't always been the North Star. 5,000 years ago, it was a star called Thuban, which I've not heard of until just now. And in 12,000 years, it will be Vega. I have heard of Vega. So there's this cool little cycle where I guess, since they didn't list any more, I'm guessing there's 3 North Stars, okay, depending on the time period, which is helpful if you want to do some Indiana Jones type stuff, I suppose, and you're looking back at some ancient manuscripts and so on and so forth. You might want to take in the year into account. Okay, so if you're looking at something that was 5,000 years old and they're talking about the North Star, well, you better look for Thuban, not Polaris. All right, everybody's favorite, Constellations. We've got a cool lab that goes along with Constellations, and we'll probably start it this week. The constellation is a sky picture, right? You look at some of these and you're like, well, how in the heck did they get this out of that? And my family likes to joke about if they just came up with the idea of constellations now, you know, we'd have so many different things up there. You'd probably have, you know, the iPhone and the, I don't know, who knows what, well, anyhow, you get the idea. We'd have much more modern things. But there's 88 official constellations. You guys will need to learn them all. And no, I'm teasing, but I'd like to think you know a handful. Okay, everybody knows a handful. And again, if not, well, then this lab will be great for you. You also, if you pay any attention to constellations, you know that the ones you know aren't always up in the sky. Okay? And that has to do with the way everything's moving out there. As I pointed out when we were talking about the celestial sphere, sorry if I'm making some noises here while I'm talking to you. I'm having a little breakfast. I apologize. As I pointed out when we talked about the celestial sphere, these stars often have no relation to one another. Sometimes they do, don't get me wrong. Okay, sometimes the stars really are right next to one another or in a line from our perspective. But oftentimes, and I think it's the two shoulders of Orion, somebody told me once, are light years apart in distance. Again, think of that in not left or right, but into the celestial sphere, if you would. One is we'll just make up a number here. Don't quote me on this, please. We'll say one is 5 light years farther away from Earth than the other one is. But because of our perspective, because of the celestial sphere we talk about, they look like they're right next to one another, left shoulder, right shoulder. When in fact the right shoulder, you'd have to go, 5 more light years or whatever number I just said. But that's meaningless at this point in life because we can't get to a closest star, let alone any other star. It's problematic just to get to planets. It's problematic just to get to the moon, heck. So until that aspect of things changes, the distances to these stars are really, I don't want to say meaningless, but they have little consequence in everyday person's life. But it's just something neat to know, okay? So these shapes in the sky, there's 88 that are officially recognized. There are 12, I'm going to jump ahead of my slide here just for a minute, that pretty much everybody knows. All right, and we'll talk about these in a moment. But your zodiac symbols, those are constellations. But where I wanted to go before that, apparently, was the word asterism. All right. And I was bummed to find out that a handful of constellations that I thought I knew weren't actually constellations. They were part of bigger constellations. And that's what an asterism is. It's a pattern or a grouping of stars that everybody knows. Okay, but they're actually not one of the recognized constellations. They're part of a larger constellation. And the example we have here is the Big Dipper. Okay, everybody could find the Big Dipper. But turns out the Big Dipper is the head, or would that be the tail? I should know that, sorry. The head of Ursa Major. To me it looks like the bear's running that way, right? So it's the head of Big Bear. Or its tail. It kind of looks like a bear tail. No, bears don't have long tails, do they? It's not biology class, so we don't have to worry about that. But point being that the Big Dipper that everybody knows and loves isn't actually one of the 88 constellations. It's an asterism. Okay? And I see a typo. I wrote what it was. Big Dipper. There we go. I wrote what it was part of instead of the constellation. And then let's say my favorite, I could find Orion. I could usually find the Dippers. But I could always find Cassieopeia. And Cassieopeia, if you don't know, I should add a picture of this in here, is the W. Okay, it's supposed to be Cassieopeia, the queen, princess, reclining in her chair. But the W is just the... How do I not have a picture of this? The W is just the 1, 2, 3, 4, the 4 brightest stars in the constellation. There's actually many more. So technically, when you're looking at the W, you are looking at the constellation Cassieopeia, but you know, we all think it's the W. So Summer Triangle is another one. So anyhow, I see I never went back into display mode. So the Zodiac. You know that astrology is not science, right? Astrology, astronomy. Two different words, two different things. But we've been doing this for so long that so many people, and I read my horoscope too, don't get me wrong, okay? I'm Virgo, I'm over here, all right? But I can't tell you what house or what was rising and what wasn't, and I don't get into it that much. But everyone knows their star sign, and that's fine. Okay, it's when we put too much credence in it that we at least leave the realm of science. I won't say more than that. So the way this works, all right, is that I had this all figured out the other day here. So this is your ecliptic plane, okay? This is that rotational disk band that we talked about. So it's one of the things I figured out, not to help you figure out your star sign here or anything, is that they really sort of seem to straddle the months. I was born in September, okay, for example. But when you look at where here's the Earth, there's the Sun. So the Sun is seen in the direction of Leo, all right? So I'm over more towards mid-September, and if you go straight across from October, it puts you at the end of Virgo, almost into Libra here. So being in the middle of September, I guess the Sun was right around here for me. And you could find your own months in there and see how that all works out. But let's do the December one since they labeled it for us here. December 1st, the Sun is seen in Scorpio. So let's go across here to, well, by golly, that says, oh, there it is. Nice job annotating this, folks. That line comes straight across from November. Well, December's not too far away. Anyhow, so this is the idea behind what star sign you are, is where the Earth was in its orbit, and where the Sun shows up in the constellation there. It's kind of cool. And if I sound like I don't know a whole lot about astrology, you're absolutely right. All right. Let's get a little closer to Earth here. Talk about the planets. We didn't know planet versus star when we go back to these early observationalists, these folks that were hanging out on a hillside or at the top of a tall tower, observing these stars. But what they did notice was that all but 5 of them played by the same rules. Okay? There were 5 objects up in the sky that moved around. Sometimes they went backwards, seemingly. They weren't always the same brightness. And they didn't know what to make of these guys. They labeled them wanderers. Okay? And today, we know that's what planet means, was wanderer. So, these 5 stars that wandered around, we came to know as Mercury, Venus, Mars, Jupiter, and Saturn. All right? Your Roman gods there. The planets are a lot closer. Okay, we'll talk more about why they do what they do here But the planets are a lot closer, and there are a couple other planets, of course, Neptune and Uranus, but we couldn't see those without telescopes. Okay, we couldn't see those without telescopes. So presumably they were named, the couple more Greek Roman gods, after after we saw them with the telescope. But it was interesting that they picked these guys first, I guess, huh? So, I'm going to try this. I've not, I'll be honest with you guys, I've learned a lot more about astronomy in the last week or two, rewriting these lectures than I have and learned in many years. I'm going to try this next time. It's a nice, clear, and warm night out. Venus has been particularly beautiful the last month or so, and I'm going to use one of my apps, which I'm going to introduce you guys to in the lab, on my cell phone. It's a great help, and it's really not cheating unless you impress people with your knowledge without letting them know that you're actually using this app. You whip it out at a bonfire and say, "Oh, look how this is." Like, wow. You're like, yeah, thanks, cool. Let them know you're using this app and spread the word. And more people learn about the sky, the better. But so anyhow, you can find this ecliptic plane that we've been talking about that seems so obscure, simply by having a few of the planets being visible on a given night. All right. So you take the sunset, or at least where the sunset was. Then you go upwards from there. Again, Venus should stick right out, okay? See if you could spot Mercury or Saturn. Spica, again, is a star I've not heard of, but apparently it's always right there, and I'm going to look for it next warm night we have. You should be able to draw an imaginary line up from the sunset through these planets here, and actually, view looking southeast, this must be a sunrise. It works at night too. Venus is morning star and the evening star. Venus is always, I don't say always visible, but she's out a lot. But yeah, if we're looking in the southeast here, this must be a sunrise. Anyhow, you draw a line from the sun, be it the sunrise or the sunset, and it should still work. And that'll give you that ecliptic plane that we're talking about, which is where your zodiac is lined up, which is where the rotational spin, which would be cool to actually see after all this talk in theory, in the lecture here, to actually see it in reality. All right, so we told you before that the Earth rotates the sun in a counterclockwise direction. Okay, that applies to all the planets. So what that means is that they move from west to east, not east to west. Okay. Remember, our sun rises and sets from east to west. The planets would be going the opposite direction of that, which they call prograde motion, moving forward. You've heard the word retrograde before, and I mentioned a couple minutes ago that sometimes the planets appeared to move backwards, right? That is what we're talking about here, and this is what, going all the way back to one of the early astronomers, dare I say Kepler, we're testing my memory here, tried to accomplish back with the geocentric. Okay, he was the first one to say, hey, if we want to make geocentric a real thing, I better make sure it was Kepler before you guys. If we want to make geocentric a real thing, we have to account for this retrograde motion. Ptolemy, my bad. I'm glad I checked. Okay, Ptolemy. He says we have to account for this retrograde backwards motion. And the reason for this, now that we know now, is going back to Kepler's laws. That's why Kepler was in my head. Going back to Kepler's laws, we know that these planets have different orbital speeds based on how far out they are. And, you know, the ones on the inside tracks just travel faster sometimes. So it looks like one is moving backwards, but it's only because the stuff around it is moving forwards. And if that doesn't make any sense, think about the last time you were sitting at a traffic light and the car next to you drifted back a little bit and you freak out momentarily because you thought you just moved forwards. That's what I'm talking about. All right. And why are we not? Planets vary in brightness. Well, there's lots of reasons for that. Okay, remember, just like the Earth, these planets do not radiate their own light. We see them because of the sun's reflective light, and that can vary based on what? Well, how far away they are from the sun, how big they are. In other words, how much how much area has the potential to be reflective, and the material at the surface is how reflective it is. Okay, not everything reflects the same. Your textbook uses the term albedo. Don't really want to worry about that now, but it's reflectivity of surfaces, and so there's a lot of factors. And a star, for the most part, is much more consistent, cohesive material. So, all right. And speaking of stars, this is one thing that I didn't put in here for some strange reason. After you're done and everything's all sealed up and wrapped up, you think of 6 more things that you want to. Love the news articles there. Sorry. 6 more things that you see that you should have added. Anyhow, twinkle, twinkle, little star, right? Stars twinkle, planets don't. That was one of the first things I learned to tell the difference. I have to be honest, it doesn't always help. But the reason that stars twinkle, and the real word is scintillate, all right? S-C-I-N, scintillate. Their light is coming from so far away. And as it travels to us, especially once it gets towards the Earth's surface, okay, it bends so many times. And because the star is such a tiny pinpoint of light, that bending of the light sometimes makes it move outside of its area, move outside of its disk, so to speak. It makes it look like it's flickering. It's moving to the left, moving to the right, moving up, down, whatever direction you want. Every time it bends, it moves a little bit, and because the star is so far away, you could actually see it changing position. With a planet, on the other hand, it's reflected light, but it still can be bent. The planets are so much closer that the reflection stays within the circular pattern, if you follow me here. In other words, the light is bending, but it's not enough to go outside of the barrier, the circle. If you could draw a circle around the planet or the star, that's what I'm talking about. So with a planet, because it's so much closer, all the variance stays within that circle and it doesn't appear to twinkle. But the star, because it's so much smaller, because it's so much farther away, the twinkling goes outside of that little circle and it looks like it's flittering or fluttering. Anyhow, twinkle, twinkle, little star. Okay. Alrighty, folks. So that is the end of the second PowerPoint for understanding astronomy.